Welcome to another video in the series about the C7000 compiler. This video discusses vector comparison and predication. My name is George Mock, and I'm your guide. This video opens with a counterexample of vector comparison, and it makes some intuitive sense that you might think that a vector comparison like this would work. After all, you can do a similar thing with addition and subtraction and so on and so forth. So let's consider it. So we have two vectors of floating point A and B initialized to some values, result that we're computing something into, doing a comparison here. It turns out you get a build time error when you try this. Well, it doesn't really make sense to compare vectors in this way because a vector is this, unordered collection of values. So this raises the question, well then, what does make sense? What do you do? This is what you do instead. So what this code does is it compares the two vectors, finally putting into the result vector all the smaller values, okay? And we're going to explain this a few lines at a time. So for the next few slides, you're going to see a repeat of this code, but one or more lines are going to be in bold, and those are the lines that we'll be talking about during that slide. This example code uses some intrinsics, CMP, LT bool, and select. Those intrinsics are defined in the header file c7x.h, and so you have to include that header file to be able to refer to those intrinsics. The intrinsic CMP LT bool performs the less than comparison for corresponding elements of each vector, and the result of that particular comparison is assigned to the corresponding element of this bool vector. Okay, and all these vectors have to have the same length, same number of elements. So that's why you have the 4 here, the 4 there, the 4 there. So let's walk through the first element of A and B. You've got 1. And -1 is 1 less than -1. The answer is no, it isn't, and so that's why 0 is assigned to the first element of the Boolean vector cond LT, and so on and so forth. So you can see that that's how this vector gets built up. The Boolean vector, you get a 0, 1, 0, 1. Let's consider the last one. -4 is less than 4, so that's why there's a 1 there. The intrinsic select assigns an element from the second or third vector based on the value in the corresponding element of the first vector, the Boolean vector. Okay, so if there's a 1 there, it's going to choose from the second vector, and if there's a 0 there, it's going to choose from the third vector. So let's walk through this exact case right here. So you go to 0 in the first element of the cond LT Boolean vector. So that means we're going to not select from A, but we're going to select from the third vector, which is B. That value is -1, and so this -1 gets copied into here, and so on and so forth. And so let's again take a look at the last one, just like we did in the previous slide. So the fourth element of the Boolean vector is 1. So we're going to choose from the second vector, which is A. That -4 gets copied into here. And so that's how the result vector is populated with all the negative values of these guys, the ones that are less than. Our example thus far used float vectors. What happens if you try to use int vectors? Well, it turns out you get an error at build time, provided you're using compiler versions before 4.0.0.sts. So the next few slides are going to explain what's happening here and give you a way to do this comparison with integer types. The best way to understand what intrinsics are available is by inspecting the header file c7x.h. So I've opened up a command line interface. In this case, it's Windows. You might call this a DOS command line interface for those of you who know what that is. And it's opened already in the directory where the header file is located. If you're running CCS, as I suspect many of you are, and you're running some variant of CCS 12, then it'll be located in TI/CCS 12.00, and then so on and so forth until you get to the directory for the compiler, in this case version 3.1.0.lts, and then /include is where the all the header files are located, including c7x.h. In the command history of this window, I've already got the commands I want to run for this little segment, so that's why you'll see me just cursoring up and down and not typing. So the first thing to do is to just get a brief look at c7x.h itself. I'm not going to get specific here, just give you a rough sense of what sorts of things are in here. You know, I've already shown you many lines, and that's only 3%. It's a big file. Okay, there's a lot here. Okay, so that's why it's more typical to do things like this. So find str is a DOS command for, you know, searching the file for this string. If you're on some variant of Unix, you would use grep instead. And what we're looking for here is, well, what's the story with the intrinsic CMP LT bool? So you get a sense of it here. You know, it works with several different sizes of bool vectors. In our example, we're concerned with bool 4, so let's restrict the search down a bit more to just, well, what's the story with bool 4? And here it is, okay? You can see that it only supports float and double types, no integer types. Which sort of raises the question, well, what about the other compare intrinsics? Do they have the same limitations? What's going on? So let's consider CMP GT bool for greater than and see what it supports. And well, it supports all the integer types, and look, it doesn't support the float types, okay? And when I say integer types, I'm talking about char, uchar, and so on. So this is how you can work out what sorts of intrinsics are supported, and what those intrinsics can do for you is by inspecting the c7x.h file in a manner similar to this. Now that we know CMP GT bool can support integer types, we can use it to implement the same operation for integer types that we did with CMP LT bool with float types. The unusual step is you have to reverse the operands. Recall in the previous example it was A, then B. Here it's B, then A. And then you use select with the operands in the usual order. I presume a few of you will want to pause the video and convince yourselves that you know, these comments accurately show what actually gets computed by this use of these intrinsics, but it really does. And comparison for other missing types can be implemented in a similar way. If you use version 4.0.0.sts or later, you don't have to worry about missing types. All of these vector comparison intrinsics support all of the types as of this version of the compiler. This next example is about vector predication, and the key lines of this example are in bold, but first I'm going to describe the lines that are around it. Please understand these lines are more descriptive than precise, as opposed to the lines in bold really are precise. This is very typical of what you would write. This other code, it's really not. What this function does is it sums up all the integer values starting at this base address for that many values, and returns it, and it does it 4 at a time, you know, using vectors of with 4 elements. This is not what you would do with a C7000 CPU. This is purely an example contrived to set up these lines so that we can talk about these lines in detail. But you do need to understand a little bit about it. So, you know, sum is set to 0. It's a integer, a vector of 4 ints, and this is how you set it to 0. And here's a pointer to one of those vectors, and it's initialized to the base address that's passed in. I'm not even showing the code that iterates through this and you know, 4 at a time sums them up. And then at the end, you sum up those 4 values in sum I4 and return it. I just want to focus on these lines here. The context of these two lines is that, okay, so the loop is over, and let's notice that the length of this array is not constrained to be a multiple of 4. Okay, you could have other lengths that are not a multiple of 4 being passed into this array, and you've done length divided by 4 times, so there might be some left over. And well, how many are left over? Well, that's given by the expression length mod 4, and then we give that as an input to this intrinsic being introduced here that creates a mask, and then we use this select intrinsic to do an addition, a final addition into sum I4. Okay, so that's an introduction to what's happening here, and in the next slide we're going to break this down in even more detail. This slide repeats the 2 lines of interest here, and then there's a table of information that helps you understand what's happening a bit better. So let's start with the expression length mod 4. As you recall, that's the number of values left in the array that have yet to be added into sum I4. Okay, and that's an input to this intrinsic mask bool 4, which returns the values that are shown in this column of the table. 0 gives you a mask of all zeros. 1 starting at the first position. Okay, what mask bool 4 returns is a mask of 1s starting at the first position, and how many 1s will there be? Well, it's given by the number that's the input. Okay, why is this useful? It's used as the mask in the select intrinsic, and this is the very same select intrinsic that was used in the previous example of vector comparison. So let's recall each of these vectors have to be the same length, and all the elements correspond. So if there's a 0 here, it's going to get the value from there. If there's a 1 here, it's going to get the value from there. So let's consider the example of, say, the input's 2. That means there are 2 values in pointer I4 that need to be added in, and they are in the first 2 positions. Okay, so that's going to get them from there, and then the last 2 positions are going to get it from the 0 here, and that taken together is what gets added into sum I4. So this operation is what we call vector predication. I'll close this video by giving you 2 references. The first one is this URL here. It's the homepage for the C7000 compiler. If that's too much for you to type in, another way to get to it is to search the internet for C7000 compiler. All the search engines I tried return this result, first, second result. This gets you, however you get there, you're at the homepage for the C7000 compiler, where you can download the compiler, access the manual, and more details like that. The second reference is to e2e.ti.com. This is for customer questions on any TI product, including the C7000 compiler. If it is a compiler-related question, it will be answered by me. Thank you for watching this video in the series about the C7000 compiler.